Hello, math humans. We're going to do 3.9 today. We're going to talk about differentials. Our objectives are that we're going to use differentials to approximate change. So the first thing we should probably go back and do is talk about a differential equation. So that might be something like dy dx is equal to f prime of x. Remember that we would cross multiply, so my differential equation becomes dy is equal to f prime of x dx. And then we talked about in previous sections that then I could integrate both sides, and when I do, I would get y is equal to f of x. Okay, and so that would be the process that we've used previously. We could either get a general solution or we could get a specific, and I think that's not the right word. I think the book uses a particular solution. Okay, so you can get one of the two types of solutions. But if we go back to here, we get dy is equal to f prime of x dx. So delta y is going to equal the true change in a value, and I'll explain this a little bit in a moment. And then dy is going to equal the approximation of the change. And then delta y is going to equal f of x plus delta x, we've seen this notation before, minus f of x. Okay, so we're going to have a difference between delta y and dy. So I want to talk about a function. Let's talk about y is equal to x to the 1/4. Oops, that's a really excited 4. So when I look at that graph, the graph would look like this. Okay, and I'm going to blow it up, and I'm going to include, this is the point 18, okay, and then the y value would be 18 raised to the 1/4. So this would be the function y is equal to x to the 1/4, okay? So I want to approximate change using differentials, and so it's similar to the concept of Newton's method. And remember that Newton's method is using successive tangents to approximate a zero of a function. So in this one, I'm going to look at the point x is equal to 16, just because it is a polite value. Well, the difference, or the change, is here. So if I do the 4th root of 16, I get that that is 2, okay? So I'm going to say that my delta y, the change in y from 16 to 18 is going to be 2. So from f of 16 is going to be 2, okay, to get to f of 18. Alrighty. So then I know for f of 18 that it's going to equal delta y, which is the true change. And I know this seems a little bit silly, but we'll talk about it in a little bit, okay? Alrighty, and notice that my delta x is also going to be 2. So this is my delta x. So the formula that I have is dy is equal to f prime of x dx, okay? Well, we've shown that, because it's super easy math, my dx is going to equal 2, so I'm going to write that here. Dx is 2, because from 16 to 18 is 2. So if I take the derivative of the function, dy is going to equal 1/4 x to the negative 3/4 times delta x, which is 2, okay? So when I do that math, okay, I get that dy is going to equal, 2 goes into 4 2 times, so this is 1/2 times x to the 3/4. That's what dy is equal to. Well, then if I substitute in my x value of 16, right, So then if I do, this is 1 over 2 times 16, because that's where the dy came from, and I raise that to the 4/3, then I get 1 over 16. Alrighty? Okay, hang on, I gotta turn my page. So then I get that my dy is equal to 1 over 16. I put a little box around that so it's right at the bottom of the page. So if I want to approximate 18 raised to the 1/4, it's going to be the original y plus my dy. My original y was 2, okay, because, f of the 16 was 2, so that's my original y, plus my dy, which is 1 over 16. So then I can approximate 18 to the 1/4 is going to equal 33 over 16, and that's putting those two numbers together. All right? So I will tell you that this is considered approximating error, and there is a huge industry for error. So, for example, if I am creating a product, and that product is for a car, there are tolerances that those parts have to work within. If it's too big, then maybe my piston doesn't work. If it's too small, then maybe the piston doesn't work as well. So manufacturing has tolerances that it has to work within to create a product that's going to consistently give a car a piston that works. So I know this probably seems a little bit confusing, so let's do an example. We only have one again today, so I'm going to let y equal x squared, and I want to find dy when x is equal to 1 and dx is equal to 0.01. Oftentimes in these problems, when you're trying to calculate error, they're going to give you a value, okay? And I want to compare with delta y for x is equal to 1 and delta x is equal to 0.01. So I'm going to write down the equation that I was given. F of x is equal to x squared, and I'm going to write down f prime of x is equal to 2x. So I know that my dy over dx is equal to f prime of x, so that's just a differential equation, and I get dy is f prime of x times dx. So I want to evaluate, so I'm going to do f prime of 1 because that's where I'm making my prediction, and then I'm going to multiply by dx, which was given 0.01, and f of 1 is going to be f prime of 1. I'm saying, what in the heck did I do? But it's right here. So f prime of 1 is going to be 2 times 1 times my delta, 0.01. And so this is going to be dy is 0.02. This is going to be my approximation of change. Okay? So then if I do delta y, that is f of x plus delta x minus f of x. I'm just going to substitute in everything I know. So I'm starting with my 1 plus 0.01 minus f of 1. So this is going to be, so I scoop my paper up, f of 1.01 minus f of 1. And I'm going to get 1.01 squared minus 1 squared, and that's going to give me 0.0201, and this is delta y. Okay, so notice that my dy I found to be 0.02. My delta y is 0.0201. So I will make a statement that the values for delta y and dy will get closer to each other as delta x goes to 0. So as my tolerance gets tighter, meaning like 0.001 or 0.0001, this would be tough considering if you were considering manufacturing, but as my tolerance, my error, my delta x gets tighter, then my delta y and my dy values are going to become closer and closer together. So if we were managing manufacturing, the goal would be to find a tolerance where these two values would be approximately the same. So for calculus, for us, for right now, you need to remember this equation, and you need to remember this equation. So the problems typically are not super difficult, but you have to know how to substitute your values in to be able to answer the question. This is just a generic statement. My comparison would just be showing that the two of these are not exactly the same. Alrighty, that is it for today. I will see you soon.